mean diffusivity because it's still running into lots of obstacles. And if you're not familiar with looking at the images, we display the primary direction of diffusion in a couple different ways. What you see most often is color, where the standard colored displays are red. Oh, sorry, this is a coronal section, this way. So red, the standard is for that to mean left to right. In this image, you can see the corpus callosum very clearly connecting the two hemispheres of the brain. Oops. Blue means up and down, superior to inferior. So you can see the internal capsule here going up and down. That includes the corticospinal tract going from spinal cord up into the brain, or the other way. And green meaning anterior to posterior. So you'll see a couple green bits here that are going into the page. And those are a couple of the other major fascicles that have been identified. Now, I just want to mention, I'll try and say it briefly, that there's lots of different things that can contribute to the measurement of fractional anisotropy. The axon membrane, the myelin, like I said, the cytoskeleton does as well. There's also things like the axon caliber. Is it a broad axon or one of the very narrow axons? The packing density. Are all the axons bundled very closely together, or is there a lot of space in between them? And the average orientation of the axons that I'll show you in a second. And I just mention that because when you read about DTI studies, often they will describe that, oh, the two groups had a difference in integrity because one of these measures is different. And it's a hard thing, yeah, we always argue over the term integrity.
I know what you're talking about.
But it's partly because it's hard to explain, well, gee, we found a difference in the measures, but what exactly does it mean? It can be a little challenging to interpret exactly what it means biologically, but as you get to know the different measurements, you can get, by combining different measurements, you can get some specifics of it. But also one example is radial diffusivity. Often if there's a group difference in radial diffusivity, papers will say, oh, it must be a difference in myelin. Yeah, there's a very good chance that it is a difference in myelin. That's one of the main things that will affect radial diffusivity. But there are other factors that can affect it as well. And so you always want to be aware of the many different things that can alter your measurements. Another one that you hear about a lot that can affect the different measurements are crossing fibers or complex fiber orientations. The ones to look at here are really just these lower panels where you can see two fiber bundles that are crossing. That happens a lot in the brain, that's not uncommon. But when you get that, again, what you're looking at with DTI is the average across everything that's in that voxel. And in a case like that, what you're going to get is an estimate that the primary direction of diffusion is somewhere in between. And you're also going to get a reduction in your FA estimate, which again is one of the most commonly reported numbers. But that might be interpreted as, oh, there's a difference in integrity. It could just mean that there's more or less axons crossing in a single place. And if you actually look at an FA image, you can see spots where we know there's big major crossing points. FA goes to 0. So it looks like there's just nothing there, and that's just an artifact of crossing fibers. And because of that, when you do tractography, tracks sometimes will not go through those points because it thinks, oh, there just doesn't seem to be a track that goes here, it must just end. And that's one of the limits that you always have to think about for tractography. This is just some of the different ways that you can measure, go about measuring, so analysis approaches. You can do a region of interest approach. Tractography, of course, is a common one. And each of these has pluses and minuses, but in the interest of time, I'm not going to go into it too much. Or I'm not going to go into it. But more just to mention, again, some of the limitations that you keep in mind. I think I learned about the limitations of the method before I learned about the method, so I sort of thought, oh my goodness, wow, you're not going to get anything. But actually, when you go and you look at diffusion images, you look at the anatomy, you looked at the tractography, it's all really quite stable and replicable. I mean, you can go in and I can say that's the superior longitudinal fasciculus, that's the internal capsule, and I know where I'm missing things because of things like crossing fibers. So it's quite replicable, but you just have to keep the limitations in mind. So I mentioned crossing fibers, and actually with tractography, that can not only lead to missing tracks, like I mentioned, but also false tracks. You can wind up, if you've got fibers that are abutting each other but go in, maybe don't cross, you can have tractography that jumps to the wrong direction, basically. So it crosses where it shouldn't cross. And so you should always be aware of what the real anatomy is when you use the method. Oh, and two important ones that I didn't mention. Diffusion imaging cannot distinguish afferent fibers from efferent fibers. So you just got to go with that or know from anatomy, which it is, if there is just one. And it can't distinguish excitatory versus inhibitory. This is just an illustration of some of the major fascicles that have been identified. Again, they're quite reliable in typical brains. Oh, they're quite reliable, but then again, there's a few that get arguments. So if you go looking into anatomy research, there's some of these big bundles that one group will say it exists, another group will say no, it doesn't. Partly because we're depending on monkey data, but also just because the historical descriptions, there's lots of reasons. Okay, so just to look at the typical development of diffusion measurement. This is looking just at the cortical spinal tract, a nice simple track. And what you see over development, this is looking 5 to 30 years of age. But as you get older, FA tends to increase. So that's mostly because you're getting more myelin. Diffusion's getting more restricted. So FA will tend to increase with development. And at the same time, mean diffusivity will tend to decline with development. That's also a lot of that to due to myelin increases, which will, again, affect the measure of RD, which is going into both of those. So they tend to go in opposite directions. And remember, we've already said that myelination continues into your 20s or 30s, so not surprisingly, you see an increase over time. Now, this is looking at infancy and what goes on in infancy. We're starting at, each column is a different age point. We're starting at birth on the far left, every 3 months up to 1 year, and then 2 years, 3 years, and 4 years. If you look at the second row, which is FA, if you just look at a very general level, you'll see that in that youngest one at birth, you see a couple of the big tracks in the middle, but you don't see a whole lot else. The internal capsule, projection fibers going in and out of the brain, corpus callosum, those are fairly easy to see, but not much else. But what you'll also see is as you go through development, you're seeing more and more of it. You'll be seeing more and more of, this is only showing us one slice level, but you'll start to see more of the association bundles, fascicles, and as you get out towards later years in adulthood, you'll start to see what we call the U fibers. So those are white matter tracks that are just going short distances, say, from one gyrus to another. So that's how they got their names. They look like a U because they're going from one gyrus to the next. Those are probably the latest to really show up and be highly visible. We also see MD in the next row, which, as I said, is going the opposite direction, starting out very bright, and then it's getting dimmer. And in this first one, it's hard to see anything other than those ventricles. You're not seeing a whole lot more structure beyond that. Now, of course, that's not to say that there aren't axons there. The axons, for the most part, are going to be in place. What you're really seeing is rapid increase in the myelin around it, which is restricting that diffusion. And here we're looking, the same age, now we're just looking at graphs of the same data, basically. And the main thing that I wanted to point out was you don't need to look at your graphs, but just the timing kind of goes along with everything else we've expected from brain development. The bundles that develop earliest and are the most mature at birth and in the first year are the projection fibers going in and out of the brain. Projection fibers will also include, say, thalamocortical projections, are fairly prominent. The corpus callosum is also one of the easiest ones to see. I think that's partly because it's just so thick with axons. Limbic pathways are also early to develop. And then the later to develop are the association tracts. There's several major tracts. I kind of skipped over my anatomy version, but there's ones that go frontal to occipital, occipital temporal, frontal to temporal. There's quite a few of those. And in one of the readings that I gave to the students that are enrolled, it looked at the different tracts in adolescence and believed that the ones that have connections with frontal and temporal lobes are the most prolonged development. And to some degree, I think that's true, if you're thinking about the association areas. So these are this is from that reading. This is white matter development, again, across adolescents and into adults. We're looking at FA. And they looked at 20 different regions. Here you're looking at mostly the larger association tracts. You see, similar to what we saw in gray matter development, actually we're seeing a fairly steep rise in those first years. So we actually are seeing a little bit of a difference in the rate of change. If we were to look just at white matter volume, we tend to see something a little closer to a linear increase. Whereas with this more white matter oriented measure, we're starting to see a little bit more subtleties in the growth rates. What are some of these? Corticospinal tract, some of the association ones are later. And I'm well over time, so I'm going to go through that. Just one more that I wanted to, one or two more I wanted to mention. This is a different one that another thing we may be able to do with diffusion imaging, tractography, if we want to look at development. This was a study that looked at tractography coming from the amygdala. So what they did here was they used the amygdala as a seed region and then did tractography to the entire cortex, actually. And what we're looking at is from their sample, they did statistical analyses. Here they're just showing us a child brain and an adult brain from that sample. And what you can see is you've got a fairly broad dispersion of where those tracks are showing up in the child, but that it's much more narrow in the adult. It's more restricted. That might be an indicator of pruning. That could be that as you develop, you're getting rid of overly exuberant connections from the amygdala to other areas. It could also be problems with motion. Because another one of the limitations we always face is making sure this wasn't one that was under anesthesia. I think I have a different slide where it was.
Do you know what the author is?
This is Sagan. Yeah, this is, we're already doing this in our sample. So we did some tractography like this too. Jan already has it probably done. Anyway, but so motion can also unfortunately cause some issues. But this is another thing that I think is quite interesting, another interesting application of the method. Is looking at the anatomy itself. So not just the measurements that you can get from it, but how broadly does one region connect to another, not just across development, but comparing between two subject groups, for instance. Just real quick to tell you what we've seen in autism to show that, again, this is another measurement that can show group differences. This is, oh, and this also lets me show you one more method of analysis. This study looked at 18-month-olds to 6-year-olds. Another commonly used analysis method in diffusion imaging is voxel-based morphometry. In this case, this is TBSS, which is track-based statistical.
Spatial.
Huh?
Spatial.
Statistics, yes. And always the S's give me. So
Yeah,
track-based spatial statistics. And what it's actually doing here, so the green is just showing you what it calls the white matter skeleton. It's just the center of all of the areas of white matter. And then it maps the measures, the FAMD, things like that, onto that skeleton to allow statistical comparisons between groups. So it allows you to align all of your subjects to a single space that's based on that skeleton. And then the areas marked in blue here are showing where they found a significant increase in FA in the autism group. So here they found, I believe, the corpus callosum, superior longitudinal fasciculus, and I think they have at least one other area where they found it. And then these are just the graphs across age, where you can again see in red is autism, where you saw actually an increased FA measure, which suggests almost like a increased maturity of those tracts in that younger age group, both in the corpus callosum on top and then in the superior longitudinal fasciculus at the bottom. And that's a tract that has connections really going through all of the different lobes and is important for language and a number of other functions. And that kind of goes along with what we saw in the volumetric, in that we almost, in autism, have, it's not literally an acceleration of growth, but some of the benchmarks seem to be hit earlier with regard to the structural measurements that we can get at.
Did they see that in the whole brain? Like they run the TBSS on all brain and then look at the differences, whatever was significant, or they did some hypothesis, select only few tracks?
In this study, and most often what I see when they're using TBSS is kind of more often a little bit hypothesis blind,
Right.
or they
Because
may
you can-
have one, but they
you
don't
don't
adjust
get-
the statistics for it.
Right.
I believe this study did the FA analysis with TBSS, so blind, and then used that as regions of interest
Okay.
to apply to the other
And
other
these are
measurements.
corrected for multiple comparison, or?
That, I think they did. I think they did, yeah. And what you find with autism studies, though, is we generally find that increase in FA in the younger subjects. Localization seems to vary quite a lot in the literature. So it's less clear which tracks in particular are affected.
Right.
Maybe more consistently the ILFs and the other association ones, but there's more.
Yeah, because sometimes it's difficult, like you can have an increase or decrease according to the tracks, and it can be difficult to interpret the results.
Yes, and that's very often one of the complexities is the interpretation takes a lot more. You can find the differences maybe, but then you got to interpret it.
Right.
Okay, so I am way beyond time, so this was just sort of a wrap-up slide. Like I said, I
What
didn't
was
think
the
we'd
one you
get to-
just skipped? That looked interesting.
Oh, this is
Okay, where's this from?
this one is from Conti, 2015. This is a summary slide of findings, diffusion findings in autism. What they've done here is we've got, so this is many different studies. Each bar is a different study. Age in months is across the bottom. Blue means that FA was higher in ASD, and red means it was lower in ASD. The width means the sample size, and there's some other things like that. But what you can see is that in general, the literature shows that FA tends to be atypically high in the youngest subjects, but atypically low as you get into older subjects. That also maps back, like I said, to what we see in various structural measures. They start out high on lots of things, but then typical development catches up. And so it almost looks like the autism group has lost something, but really it's most often that the TD group, the control group, has caught up and surpassed them for some reason. So there seem to be differences in the timing of development in autism. Okay. So this is, again, just a summary of all of that. And I am just going to say that I am now 15 minutes over time.